Start the second talk from this conference. And for the second talk of this conference, we have Andrew from the University of Alberta, talking of Hodge numbers of hypersurfaces in toric varieties and Landau-Ginzburg models. Andrew?
I'd like to thank the organizers for putting on this really nice conference.
No se oye mucho.
Okay, so yeah, I'd like to thank the organizers for putting on this conference and inviting me to speak. I'm coming from about 40 degrees Celsius lower than this, so I'm happy to be here. Okay, so yeah, I'll talk about Hodge numbers and hypersurfaces and toric varieties. Oh, even more. Okay, there's a microphone around here, isn't there? Okay, so great. So okay, let's see this first. Okay, so just an outline. So first, I'll talk about so mirror symmetry for fauna varieties and sort of what I call quasi-fauna varieties. I don't know if there's actually, I don't have an actual definition in mind, but these are things that look like fauna varieties. Interesting. Okay. Anyway, this will be short. I'll talk about constructing Landau-Ginzburg models for these. So these are sort of the mirrors of these fauna varieties. So this is not working. Okay, sorry, I should have. Yeah.
Just do it again. It happens sometimes. Are you using Adobe or what?
Full screen, the last one.
Yeah, okay. Great, so then I'll talk about Hodge numbers and hypersurfaces. Oh, now it's just going. Let's pause this, hopefully this works. Now this doesn't. Oh, I'm doing this.
It's not working.
Yeah, no, this isn't working. Great, then I'll talk about the relationship, sort of an application of the results about Hodge numbers and hypersurfaces, sort of counting components, fibers of Landau-Ginzburg models. Then I'll relate this to K3 surface vibration on cloudy L3 folds. So we'll see how that goes there. Okay, so just to recall, so for a cloudy variety, sort of mirror symmetry predicts that, that there's sort of this mirror cloudy variety, so for most of these things. And this should sort of be a duality in the sense that it exchanges complex data about one cloudy variety with sort of symplectic data of the other cloudy variety, and vice versa. Okay, so as an example, the quantum cohomology of W should be related to the Gauss-Minian connection, or periods, or sort of variation of Hodge structure obtained by deforming the other, its mirror cloudy variety. One other thing that should occur is there should be a relationship between the bounded-derived category of the Fourier category of W. So the bounded-derived category is based on algebraic geometry, bounded-derived category of coherent sheaves, and the Fourier category is something based on symplectic geometry. And sort of maybe this is sort of like a result of the other two, or one of the other two, take your pick. Is that there should be sort of a Hodge number duality between V and W. So essentially, you take the Hodge diamond of one of these things, you put your lines across the middle here, and you flip it across this line, and this gives you the Hodge diamond of the variety. Okay. But for fauna varieties, the situation is slightly different. There is a form of mirror symmetry for these things, but this sort of, instead of replacing X with the fauna variety, you sort of replace it with the Landau-Ginzburg model in the mirror. So what is this thing? So this is a pair Y, a variety Y and a map W, where so Y, as I said, is a smooth d-dimensional. I guess in my sense, it's a quasi-projective variety. In general, this doesn't have to be quasi-projective. But there's going to be a map W on this thing called a superpotential, which is just a regular function on Y. And so for mirror symmetry to hold between sort of a fauna variety and a Landau-Ginzburg model, we expect a bunch of different things to sort of to be there. So we want sort of compactification of this variety Y to a manifold Z, so that W extends to a map F from Z to P1. So this was originally just a map to C or to A1. We want the existence of a meromorphic section omega Z with sort of logarithmic poles along the fiber at infinity. So this thing we added to get Z, we want just sort of log poles along this thing. we want this to vanish nowhere along the rest of y. So this is sort of a log cloudy out condition. And so the other condition is that sort of this encompasses mirror symmetry. And this isn't a definition, this is just sort of expected properties. But sort of this gives the fibers of this superpotential are cloudy out varieties, and that they're actually mirror dual to the anticanonical hypersurfaces in the Fano variety we began with. So these are just things that come out of the okay. So what sort of relations should X and this Landau-Ginzburg model satisfy if they're, say, homological mirror to each other or something like this? Well, the periods of Y, so you think about this thing as sort of a vibration over C. So you look at a small disk around infinity, then the periods of Y, of fibers of Y around there should be related to the Gromov-Lipnik variance of X. There's a form of homological mirror symmetry for this as well. So the boundary-derived category of coherent sheaves on X should be related to the directed Chi category or Chi-Seidel category of the Landau-Ginzburg model. On the other hand, there's another sort of, there's a flip version of this, where you relate something like the categoric matrix factorizations of this pair here to the Chi category of X. Sort of according to work of Katsukov and Cinvestav-Campinas, what you can get out of this is sort of a version of Hodge number mirror symmetry. So this is the last thing I wrote. Anyway, so there's a relationship between the Hodge numbers of two different Clavier varieties, and sort of there's a version of this for Bonos as well. But sort of instead of, what are the Hodge numbers of a pair like this? It's not really clear. So they gave a definition of this. So what they do is they define what they call sheaves of f-adapted logarithmic forms on compactation z of y. So I think they're denoted something like this. So d infinity is the thing you add to get the compactification in sort of my sense. So I'm taking a relatively compact blending, I guess. And so the Hodge numbers of these things are just ranks of cohomology of these sheaves, sort of in the same sense that the Hodge numbers of say any variety is just sort of get rid of this, and that's the Hodge number of the cube. So maybe I'll say, so this is just a subsheaf of the sheaf of logarithmic forms of logarithmic poles at the infinity. With sort of nice properties with respect to the differential df. F is a function on y, so this is sort of nice. So what Hodge number mirror symmetry for Fano varieties predicts is that, so the same thing holds between these new Hodge numbers and the Hodge numbers of y, or sort of x. So Katsukov and Cinvestav-Campinas show that if you take the sum of these things across n, this is just the nth cohomology of the relative, the nth relative cohomology, the rank of the nth relative cohomology. So here V is a smooth fiber of the vibration W, and it's just as usual. So just to take an example, and this is kind of a little bit of a non-example, but it's also an example. So let X delta be sort of a maximally projective Peckin partial resolution of the toric Fano variety. So associated to a reflexive polytope, what you can do is you can sort of, you get a Gorenstein toric Fano variety. And so this thing has, a priori data singularities, but by sort of taking a refinement of a related fan sort of in a nice way, Batchev shows that you can get a Prepin resolution of this Gorenstein toric Fano variety, which has only terminal singularities. So this is what I mean by the NPCP resolution of a toric Fano variety. So let F be some sort of Laurent polynomial, which is just the functions from D copies of the algebraic torus to C. And we're going to let Bf be the vanishing locus of F. Okay, so this is a priori just some sort of open part of the Plática variety. So using the results of Batchev, which built heavily off of work of Danilov and Kavansky, actually this is both work of Bacharev and Bacharev dies. What you can show is that the sort of the rank of this cohomology group, the relative cohomology group here, is essentially the sum. Right, it's the sum of the stringy Hodge numbers. So the point is, you take the cohomology going across the sort of the relative cohomology group. You take the you take a column of the Hodge sort of Hodge diamond, or the stringy Hodge diamond of this toric variety. And so the sum across this column gives you the same thing as the relative Benny number here. So even more than this, what you can do is you can sort of relate the Hodge numbers. So actually, I should note that these stringy Hodge numbers are exactly the Hodge numbers in the case where x delta is smooth, and in sort of the non-smooth case, they're sort of the right replacement for Hodge numbers for mirror symmetry. Right, so if you take the natural Hodge filtration on this thing, so this thing is just the relative cohomology of some some variety with respect to another variety. So this thing has a sort of canonical mixed Hodge structure. If you take the graded pieces of the Hodge filtration of this mixed Hodge structure, you actually recover the stringy Hodge numbers of x delta. So you get this.
So isn't the version of the left still?
Which one?
This HPQ is equal to HD minus QT. If we use the left variety, then this number of the complement, right? So it is the left-hand side is essentially the homology of the complement.
Here's a complement, C star minus the complement. It's not quite. I mean, so
Not quite, but
there's some modification to make. I mean, so that's what Bacharev actually computes in his Duke paper in '93. Yeah, exactly. I mean, this is essentially what Bacharev computed in '93. This is very little extra going into that. Yeah. Okay. So sort of on the other end of the spectrum, so in the case of Foto varieties, what you get is that all Hodge numbers vanish except for the HPPs, right? On the other hand, if you look at a Foto variety so that basically this thing is non-zero, the idea is so the question is, what does sort of mirror symmetry predict for for the Landau-Ginzburg model of that variety? Okay. So if x is Fano, then these two Hodge numbers vanish. Thus, we should have that this is equal to H2 of the relative cohomology where this Landau-Ginzburg mirror is. Okay. So this just comes from sort of the slides back. And the theorem that sort of goes along with this, I mean, this tells you how to compute this for I guess technically sort of for what should be the Landau-Ginzburg model of YW. So this tells you that if you have sort of a smooth, relatively compact vibration, so that the generic fiber is a Clavier variety, sort of in the sense that this is vibration over A1. And so if you assume that for this, there is a compactification like the one that we sort of asked for a couple slides back, and so that this H1 is 0. And so just as notation, let sigma be the critical locus of the map W, then what you can do is you can do this. You can compute this relative, this Hodge number, or this Benny number, sorry, just by taking the sum of all sort of irreducible components and the visorial components in fibers of the map W. So for each singular fiber, you take the sum of all irreducible divisors in that fiber, and you subtract one. Take the sum of all of this, and this gives you the Hodge number. Okay, so this is turned sort of, the idea is to now, sort of build Ginzburg models for specific Fano or sort of not quite Fano, but almost Fano varieties. Compute their Hodge number, this Hodge number here, sorry, and then relate it to this just by sort of counting. I guess I have a laser pointer here. I don't need to screech over. Anyway. Okay, so right, so that's sort of the goal. sort of a first approximation to mirror symmetry, I guess. Okay, so as I said, the problem is first the problem is to construct, prospective Landau-Ginzburg models for these Foto varieties. And then what you do is once you have this thing, you just count components in singular fibers and try to see how they relate to the Hodge numbers of the Foto you get. Okay, so Victor Przybylski has done a lot of work on this. So the first thing he kind of did, I think it was several years ago now, is that he took all the rank 1 Foto threefolds. So he computes to each of these Foto threefolds. What he does is he computes sort of nice Laurent polynomials. So these are Laurent polynomials, so that the periods of the fibers of this Laurent polynomial, thought as a map to C, the periods of these things sort of have nice properties with respect to, say, the quantum cohomology or Gromov-Whitman variance of the original Foto variety X. So he then sort of compactifies this to a fibration over A1 with compact fibers, which are quite singular. He resolves this in sort of a nice way, and then he counts components in the fiber over 0, and he shows that this Hodge number duality actually holds. So if you put the H to 1 of each of these Foto threefolds, then this is exactly sort of the count of the number of components in singular fibers of the Landau-Ginzburg model. So subsequent work so Victor and Konstantin Shramov have showed that if X is a complete intersection in Pn of K hypersurfaces in Pn, then so what they do is they do the same thing. They take a nice Laurent polynomial, they compactify it to a hypersurface in here, so that the map W is just a projection onto A1, and then they resolve singularities of this thing and count the number of components. So in this way they sort of verify this part of mirror symmetry for complete intersection. Sorry, I should say complete intersection of Fotos in Pn. So you have to make sure that some of the degrees is less than n plus 1, I think. Less than or equal to. Okay, so this is what I just said. So the goal here, and so what I want to do is I want to describe a way in which you can sort of, a way to do this for sort of general complete intersections and toric varieties. I mean, I haven't quite gotten there yet, but I can do it for specific hypersurfaces and toric varieties. So the way to do this is to sort of take construction given by Gimental, Landau-Ginzburg models, and sort of soup it out in a way that actually that this counting of components in singular fibers is related to the Hodge numbers of the Landau-Ginzburg of the variety you start with. Okay, so just as setup, we'll let delta be a reflexive polytope living inside of some lattice. E1 to Ek plus 1 is going to be a net partition of this polytope. And so just as notation, we'll let delta I be the convex hull of all of these points n0. Okay. So what does this mean sort of in geometric terms? So in terms of the geometry of toric varieties, each, as I said before, of each reflexive polytope delta, there is a toric variety, toric Foto variety called P delta. This is sort of bad singularities, or possibly not that bad, but not so nice singularities. And to each vertex of delta, there's a torus invariant variety, divisor of P sigma in P delta. Okay, so the way we've chosen the EIs is so that if you take the sum of all of these things, this divisor is Cartesian semi-empty. Okay, and so another just fact from toric geometry is since we've taken a partition of all vertices of this polytope, the sum of all of these things, if you take the sum over all vertices of delta, this sum is going to be the anti-canonical divisor in the toric variety. Okay, so we'll define line bundles Li associated to each EI. I put in J there, but I guess that's odd. So since it's Cartier, we can do this. And we'll let S1 to Sk plus 1 be generical sections of the line bundles Li. So S1 is a section of L1. So we'll let X hat be the complete intersection determined by taking the intersection of sort of the vanishing loci of S1 to Sk. So notice we're leaving out the k plus 1 in P delta. So when you do this, so if you take the adjunction formula, what this tells you is that the anti-canonical bundle of this complete intersection here is sort of the restriction of Lk plus 1. So this is an effective line bundle, you know, and it's sort of it's base point free because it's also semi. Okay, so this is nice, or at least the power which is base point. So this is nice. These are things that sort of look like quantum varieties because phonos have an anti-canonical line bundle with sections and one. So these are things that sort of are weaker than phonos, but are sufficient for my purposes, at least combinatorial. Okay, so X delta again is going to be the MECP resolution of P delta. So this is just a nice crepind resolution of P delta, or partial resolution of P delta with only terminal singularities again. And we'll let X be the pullback of X hat to X delta. So this is just a pretty interesting. So what this does is this sort of partially resolves the singularities of X hat, so that in X there's only terminal singularities. And there's also a crepind resolution of X hat. So Giventhal gives a way to compute the Landau-Ginzburg model of this X. So this is given sort of first approximation by complete intersection in a torus C star to the D, and this is going to be a book with just sort of a regular function. So to do this, it's sort of a very similar process. Actually. So this is given by this complete intersection inside of the torus again. So we'll represent sigma. So this sigma is going to be a point inside of these lattice polytopes. So sigma is this point in point B1 BD. Then we'll define monomials in this Laurent polynomial ring given by this thing here. So it's just xi to the bi. And here A sigma are just sort of generic complex constants. Okay, so this is from I from 1 to k. So that's use the k plus first piece that we didn't really use in the construction of X, but sort of is necessary here. So the potential is the description of this Laurent polynomial. So it's defined essentially in the same way as that. Okay. So what Giventhal proves is that this thing has quite nice properties with respect to relating periods on one side or oscillating integrals on one side, and sort of quantum periods or quantum cohomology or Gromov-Linden invariance on the side of X, on the quasi-phonos. However, it's if you we kind of cheated before in the toric case. We took a torus and then we were able to show that sort of this Hodge number near symmetry holds. But this won't work in this case. Even though this is not relevant to the fact, if we try to count the fibers over 0 of this sort of Landau-Ginzburg model, we almost always sort of
periods in the sense of conceptions again. Period. What is period? In the sense of conceptions again.
I'm not too familiar with that, but I would guess no. I think it's just regular periods as a family of varieties. So the solution to this is just to take a compactification of this y0 in sort of a nice way. So by the construction of Batcher and Borisov, by the mirror symmetry construction that they give, the fibers of W0, this map, these are just complete intersections in sort of, well, they admit, these are the Batcher-Borisov duals of the complete intersection associated to the net partition delta 1 to delta k plus 1. So if you take the complete intersection in the definition of X here, in the definition here, if you take to k plus 1, this is now a Claudian variety. And so Batcher and Borisov propose a construction of the mirror dual to this thing in some sort of combinatorial way. And what you get are just the fibers of W0. Okay? So they compactify naturally to X nabla, where nabla is again some sort of polytope associated. I mean, this is a polytope determining a toric variety is reflexive. Right, they're just completing associated to this. So there's basically what you can do is, since this is just a family of complete intersections in this spark variety, you can compactify this thing to a sort of naturally to a hypersurface in here, or complete intersection in here. And so the superpotential in this case will just extend to projection from this complete intersection onto the A1 factor. And we'll just denote this by W, and we'll denote by Y the compactification of this guy to this. Okay, so just to look at the properties of what you get out of this. Y has a worst Lorentzian terminal. So this is sort of the best you can really hope for without without sort of messing too much with the canonical bundle. So you can find sort of a nice compactification of Y to a variety Z, so that the projection W, or the map W, extends to a function of 1. And so that the anti-canonical bundle of this Z is equal to F for a fiber of this map F. So this sort of means that there's a section of the anti-canonical bundle of Z, I think, step condition, which has simple poles along components of the image of infinity, and which is non-matched answer. So this is sort of, this is sort of a log Calabi-Yau compactification with terminal singularities. So that's exactly the best you can really hope for. Right. Just as in the case of Calabi-Yau varieties, so the reason you get singularities is, first of all, a minimal log program, but second of all, it's because we're using sort of resolution of singularities in toric varieties, and this can't always get a correct, smooth, perfect resolution of toric on variety in dimension higher than 3. Okay, so let's get this slide. Right. So now so we built this nice Landau-Ginzburg model, and so the goal is to check that the number of components in the fiber over 0 of this thing sort of correspond nicely to not just the fiber over 0, but all the fibers correspond nicely to so the Hodge numbers of the complete intersection we started. Okay. So I tried to do this in general. I think in general, if you take this Landau-Ginzburg I've constructed, you try to compute components of fibers, this can be kind of difficult, just given the structure of toric intersection theory and things like this. But if you restrict to the case where x hat is an ample hypersurface in E delta, so then basically, everything simplifies quite nicely. This is in a sense a very sort of baby case, but it's also fairly broad. Right, so Batchev-Borisov, I don't know if 96 is the right number here, I think it's 94 or 95. But Batchev and Borisov give a construction which you can alter, which tells you exactly how to compute this Hodge number of complete intersection when it's a complete intersection of ample hypersurfaces in P delta. So this is then the resolution. And when you restrict to the case where x hat is an ample hypersurface in P delta, this becomes extremely simple. And it's easy, you just sort of, right, so the theorem here is that in the case where it's an ample hypersurface in P delta, then it's exactly true. So this is sort of the stand-in for the Hodge number here, or is the Hodge number. And this is different. This isn't exactly, what I predicted, right? Maybe I won't do it. But sort of the prediction is that this is not just so this is the number of irreducible components in the fiber over 0. But what mirror symmetry predicts is that this should be equal to the sum of these things minus 1 over all bad fibers of the Landau-Ginzburg model. So really sort of in the case where you have an ample hypersurface in P delta, you take some sort of perfect resolution. It seems to be saying that the bad fibers, so the worst fiber, there's only one really bad fiber, and that one's the fiber over 0.
So what's the relation of x hat on x? One is the resolution of x?
Yeah, x is resolution of x hat.
X.
Yeah. Right, so yeah, so this is no longer an ample hypersurface in the resolution of this.
And once again, row 0 is what is row 0?
Row 0, this is the number of components in the fiber over 0.
W.
So as I said, the proof of this theorem is just combinatorics on both sides. On the Bachelor-Borisov, give a combinatorial count on this, and then you count the number of components here, in the same sort of really use toric intersection theory. Again, basically do the Bachelor-Borisov, and you show, by hand that the numbers coincide.
So W is a function on the toric variety or on some?
It's a function on Y.
Which is a toric variety?
It's a complete intersection in the toric.
It's a complete intersection inside.
Yeah, inside of an open toric. Yeah, so right, so I mean that's how to do it. It's kind of the simplest possible way. You can imagine that possibly you could basically extend. So this is Bachelor and Boris have sort of a series of papers on mirror symmetry for Cloud varieties. This uses one of their less successful papers, but they have a very successful paper that basically shows that Hodge number mirror symmetry holds for pairs of complete intersection Cloud-Yavs and toric varieties. And one can imagine that sort of extending this sort of result, you can actually use the very heavy machinery that they have in that paper to prove Hodge number mirror symmetry for Landau-Ginzburg models and phonos, or sort of quasi-quite phono varieties. So as a corollary, as I mentioned, we have, this isn't even an inequality, we just have an inequality between H2 of the Landau-Ginzburg model and H1, this Hodge number here. Yeah. As I said, this implies that all the sort of the really badness of this Landau-Ginzburg model is in the fiber over 0. Right, and so you can ask, how generally is this true? And the answer is that it really depends on X hat being an ample hypersurface in P delta. If you sort of move beyond this, you can easily find examples where this does not hold. Right. So as an example, also just note that being phono doesn't make any difference. So if you take a cubic threefold blown up at a cubic curve, what you can do is so take the cubic sitting inside P4, take two hypersurfaces in P4, and blow P4 up at this P2. This is again a toric phono fourfold. And once sort of the if you pull back X prime along this map, what you get is X blown along a cubic curve. Right. So this is an ample inside P, the blow up of P4 at this P2. And you can check that H12 of this thing is equal to 6. If you look at the Landau-Ginzburg model of this thing, the fiber over 0 has only 6 components. So row 0 minus 1 is equal to 5, which is not equal to H12. But you can look at sort of all the other fibers of this Landau-Ginzburg model and find that there's one where there's sort of two different, has two irreducible components. So this sort of makes up for the fact that sort of you're missing one. Okay, so this is just sort of an example to see how the theorem can fail. So how much time do I have? Right, so I want to give kind of an application of this to Cloud-Yavs varieties, and so my entire discussion here is probably going to be restricted to Cloud-Yavs threefolds. But so if you sort of look into mirror symmetry, what you can get is you can get a prediction that there's a relation between what I'm going to call Turing degenerations of Cloud-Yavs varieties and fibrations on the mirror dual Cloud-Yavs variety by codimension 1 Cloud-Yavs. So Turing degeneration is a degeneration. It's just some sort of smooth family V over U with sort of algebraic fibers over a small disk in C, so that the preimage of U inside of this family is a union of two quasi-phonic varieties, X1 and X2. So these are things that have Hodge numbers that look like Hodge numbers of phonos and have anti-canonical Cloud-Yavs, sort of there's a section of the anticanonical bundle which is a Clavia prime. So we want these x1 and x2 to meet along meet with normal crossings, and we want the intersection to be a hypersurface, which is anticanonical x1 and x2. So this is a smooth hypersurface. And we want the generic fiber of this vibration tide to be a Clavia variety of W. So this is what I call a Turing generation of W. Okay, so in the following, we're just going to take a case with W. So a threefold, and this big family V is a fourfold. Okay, so we can use sort of toric geometry to construct these sorts of things. So the idea is that if you have a polytope delta, you take the toric family variety associated to this thing, and then you can get a Turing degeneration from any net partition of delta. So what do I mean by this? Well, we're going to take S1 and S2 to be sections of the line bundles L1 and L2 as defined above. These are associated to pieces of our net partition. And we're going to take a section of the anticanonical bundle of this thing, which turns to smooth Clavia threefold. So this will give you, I mean, so by construction, L1 tensor L2 is equal to the anticanonical bundle of X delta. So this is the section in X delta. So this is all just the pencil sections in, sorry, not X delta, in the anticanonical of X delta. So we get a pencil like this, which gives a degeneration from sort of the generic fiber, which is just some sort of Clavia or smooth Clavia, to be, when t is equal to 0, we just get this. So the degenerate fiber over t equals 0 is just the union of x1 and x2, where these are sort of hypersurfaces determined by sections S1 and S2. The problem with this thing is that the total space of this degeneration is not smooth. There's going to be singularities in sort of the central fibers, or where we're really interested in looking at this. So one can sort of do standard things and resolve the singularities of this degeneration. So take S1, S2 to be very general sections. Then we obtain a Turing degeneration, which I probably should have called Phi, where the generic fiber is the anticanonical hypersurface as before. But now the fiber over 0 is no longer just x1 union x2, but this is sort of x1 meeting normal crossings along some sort of divisor in x2, or sorry, x2 tilde, but x2 tilde is the blow up of x2 along some curve, and I get it this way. So it's W, the generic fiber intersect x1 and x2. Oh, this is x delta. Okay. Okay, great. So what you can prove is that sort of prediction I sort of waved my hands at in the beginning, that sort of these Turing degenerations correspond to vibrations on the mirror is essentially true. So if you take a hypersurface in X delta for a four-dimensional polytope, then to any net partition, you're given a Turing degeneration of this toric hypersurface. Okay. And on the other hand, when you sort of run this through, Bachelor's mirror symmetry construction, plus a bit of other geometry, what you get is that you can find so V is the Bachelorov dual to this thing, or one of the Bachelorov duals to this thing. Then you can sort of find a Clavia threefold, which is birational to that Bachelorov dual, so that there's a vibration on this thing by K3 surfaces. And this is done in a very canonical way. And so, I won't say too much, but there is sort of a mirror symmetry going on between the fibers of this vibration and the intersection of x1 and x2. So x1 and x2 is a complete intersection of K3 surfaces. So it's this sort of, you see, it's kind of interesting because you're seeing basically three different kinds of mirror symmetry here. You're seeing mirror symmetry for the Clavia or threefold. You see mirror symmetry, I'll explain this later. You see mirror symmetry for the phonos, and you see mirror symmetry for the fibers of the vibration of the mirrors. Okay. Right, and so I guess this is a suggestion of Turin, is that sort of there should be some way to see this Turin degeneration, the K3 vibration that we get on we had. Right, we should be able to see the structure of the phonos or the mirrors of the phonos sitting in there somehow. And so that's what the next theorem says. Right, so if we take C to be this curve, so this is the curve you blow up x2 along to get x2 tilde. So then we can see basically pieces of data corresponding to all three of these things. So when we look at the idea is that when we look at the K3 vibration that we get on X, or the vibration by K3s that we get on basically the Bachelet dual to W, we see pieces of information with C, X1, X2, sort of in this way. So if L1 and L2 are both ample, so this is an ample. This allows us to apply the theorems that we got further back. Then if we compose, this is again the computation of the number of components in the fibers of the vibration on the dual, in this case the Bachelet dual. Then these things correspond to, first of all, the genus of the curve C that we blew up along, and the H12 values of each of the component quasi-phonos in the Turin degeneration. Right, so this is kind of a really, I think it's really kind of cool. So this shows that there's nice vibrations on claudias that you get via mirror symmetry, and that these vibrations really do sort of, they carry very coarse information about the Turin degeneration, but it's still there. I mean, it's very coarse form.
You have 10 more minutes.
Okay, well, I might not use those 10 minutes. Yeah, so that'll be it, actually. Oh, I can give an example, I guess. No.
Any questions? Well, you don't have more questions. Of course, now we have time for discussion, and then lunch will be at 1 in half an hour.